the star that started looking back. For centuries, humanity believed that the most terrifying thing about the universe was its silence. The night sky stretched above every civilization that had ever existed, a vast ocean of distant stars burning quietly in the dark. Astronomers pointed telescopes upward for generations and found only distance, radiation, gravity, and the slow mechanical dance of celestial bodies. Even after humanity learned to send machines beyond its own atmosphere, the universe still appeared indifferent. Planets orbited their stars with mathematical precision. Galaxies collided over millions of years, and black holes swallowed light without any sign that anything in the cosmos possessed intention or awareness. That belief began to fracture the year the observatory network completed the Helios array. The array was the largest astronomical listening system ever built. Thousands of synchronized telescopes were spread across deserts, mountains, and orbital stations, all connected to a single analytical intelligence designed to monitor stellar activity across enormous regions of space. The system did not merely observe stars. It studied them continuously, measuring their fluctuations, recording their magnetic fields, mapping their radiation patterns, and modeling their internal dynamics. The goal was simple: to detect early signs of stellar collapse, gamma bursts, or cosmic events that could threaten Earth decades or centuries in advance. For the first year of operation, the Helios array confirmed what astronomers already knew. Stars lived predictable lives. They formed, burned, expanded, and eventually died according to physical laws humanity had studied for generations. Even the violent death of a star followed patterns that could be simulated with astonishing accuracy. Then the system detected something that did not behave like a star. The anomaly was located nearly 4,000 light-years away in a region of space that had been considered relatively quiet. The object had originally been cataloged as a red dwarf, a small and stable star with very little variation in brightness. But when the Helios array began recording its emissions with higher precision, analysts noticed that its radiation output fluctuated in a way that did not match any known stellar model. At first, the fluctuations were subtle, slight variations in the frequency spectrum, small irregularities in the star's luminosity, variations so minor that earlier telescopes had dismissed them as sensor noise. But the Helios array was far more sensitive than anything that had come before. When the data was processed through the system's predictive engine, the pattern became impossible to ignore. The fluctuations were structured, not random, not chaotic, structured. The radiation pulses repeated in cycles that lasted precisely 13 minutes. Each cycle contained small deviations from the previous one, as if the star was slowly altering the pattern of its own emissions. Astrophysicists spent weeks attempting to explain the phenomenon using conventional models. They simulated internal stellar convection, gravitational disturbances, even the possibility of an unseen exoplanet orbiting close enough to disrupt the star's outer layers. None of the models worked. Because the pattern was becoming more complex over time, the star was not merely fluctuating. It was changing the structure of its radiation in ways that resembled a signal. At that point, the anomaly was classified as a possible extraterrestrial transmission source. The idea that a civilization might be manipulating stellar energy to produce detectable signals was not entirely new. Some theoretical physicists had proposed that advanced species could use stars as communication beacons, modulating their light output to broadcast messages across enormous distances. But the Helios anomaly did not resemble a message. Messages repeat. Messages stabilize. Messages remain consistent once the intended pattern is established. The anomaly did the opposite. Every new cycle introduced variations that made the signal more complicated. The star was not repeating a message. It was learning. The discovery triggered an international effort to study the object in greater detail. Observatories across Earth and orbital platforms redirected their instruments toward the distant star. The Helios array began collecting data continuously, feeding it into an artificial intelligence system designed to detect mathematical structures hidden within complex signals. For several weeks, the AI attempted to decode the radiation patterns. The system identified thousands of repeating sequences, nested layers of modulation, and harmonic structures embedded inside the signal's frequency shifts. But every time the AI isolated one layer of structure, a deeper one appeared beneath it. The signal behaved like a fractal, an endlessly unfolding pattern that revealed new complexity the longer it was studied. And then something even stranger happened. The star's fluctuations began responding to the analysis itself. Every time researchers adjusted the AI's algorithms to examine a new layer of the signal, the next radiation cycle altered slightly. At first, the variations were small enough to dismiss as coincidence. But as the days passed, the correlation became statistically undeniable. The signal was adapting to the way it was being studied, which implied something that should have been impossible. The source of the signal somehow knew it was being observed. At 4,000 light-years away, the research teams attempted to maintain scientific caution, but privately many of them began considering a far more disturbing possibility. If the anomaly represented an artificial phenomenon, the intelligence responsible for it would have needed to anticipate how human technology would analyze stellar emissions thousands of years in the future, which meant the signal might have been designed specifically for observers who did not yet exist when it was created. That possibility was unsettling enough. But the real horror began when the Helios array detected the first synchronization event. One of the orbital telescopes had been equipped with a visualization interface that converted stellar radiation patterns into three-dimensional models. The purpose was purely analytical. Complex signals often became easier to interpret when transformed into geometric shapes that could be examined spatially. When the Helios anomaly's data was processed through the visualization system, the result was something no one expected. The radiation fluctuations formed a structure, a vast rotating geometry composed of layered spirals and intersecting planes. The shape shifted slowly as new cycles of stellar emissions were added to the model, expanding outward like an enormous mechanical organism assembling itself piece by piece. The longer the signal was studied, the larger the structure became. But there was something wrong with it. The geometry appeared incomplete. Several segments of the structure were missing, leaving gaps in the pattern that the system could not fill using the existing data. The AI attempted to predict what the missing sections should look like based on the surrounding geometry, but the results were inconsistent. It was as if the signal required information that had not yet been transmitted. Then a cognitive scientist reviewing the visualization noticed something disturbing. The incomplete sections of the structure resembled neural pathways. More specifically, they resembled the patterns formed by human brain activity during complex spatial reasoning tasks. The resemblance was strong enough that researchers conducted an experiment. They connected the visualization interface to a neural scanner and asked several volunteers to observe the model while their brain activity was recorded. As the volunteers studied the rotating structure, the missing sections of the geometry began to fill in, not with data from the star, with patterns derived from the volunteers' neural activity. The signal did not contain the complete structure. It required a human mind to finish assembling it. That discovery should have ended the experiment immediately. Instead, it accelerated the research. More volunteers were brought in to examine the structure. Each observer's brain activity contributed new fragments to the geometry, gradually filling the gaps in the pattern. The visualization grew larger and more detailed with every observation. But as the structure approached completion, the volunteers began experiencing unusual neurological effects. Headaches, disorientation, vivid dreams involving enormous shapes moving through darkness. Brain scans revealed unusual synchronization between regions of the volunteers' cerebral cortex, patterns that had never been recorded in normal cognitive activity. It was as if their minds were briefly aligning with something outside themselves. Then the Helios array recorded the event that ended the experiment. The distant star's radiation output spiked dramatically for exactly 27 seconds. The spike contained a burst of frequency modulations far more complex than anything previously recorded. When the new data was added to the visualization model, the structure became complete. For the first time, the geometry formed a closed shape. And in that moment, every volunteer observing the model lost consciousness simultaneously. Their neural scanners recorded one final pattern before their brain activity collapsed into silence. All of their minds had synchronized perfectly, across separate rooms, across separate monitoring systems. Their brains had briefly become parts of a single network. Medical teams managed to revive most of the volunteers hours later, but none of them could remember what they had experienced during the synchronization event. The Helios array, however, had continued recording the star, and the signal had changed again. The radiation pattern was no longer expanding. The cycles had stabilized. The fractal complexity had stopped growing. The signal had reached its final form. Astronomers studying the data noticed something that made several of them leave the observation room without speaking. The new radiation cycles contained a repeating pattern embedded deep inside the signal's harmonic layers. A pattern that matched the neural synchronization recorded in the volunteers' brains. The star was now emitting a signal shaped like human thought, and the implications of that discovery were almost unbearable to consider. Because if the signal had required human cognition to complete its structure, then the intelligence responsible for it had not simply transmitted information across space. It had designed a process that would slowly guide an observing species toward constructing a specific pattern using their own minds. And once the pattern was complete, the signal had changed, which suggested the process had achieved its purpose. The Helios array continues monitoring the distant star to this day. The signal remains stable, unchanging, but something else has begun appearing in the network's data logs. Occasionally, the system detects brief anomalies in the star's radiation cycles, fluctuations lasting less than a second, too small to affect the overall signal, but complex enough to resemble information. The anomalies occur most often when researchers are analyzing the synchronization data recorded during the experiment. No one knows whether the fluctuations are random, or whether they represent something far worse. Because if the signal was designed to teach a species how to construct a particular pattern of thought, then the experiment may not have ended when the volunteers lost consciousness. It may have ended when the pattern was successfully transmitted back. And if the star is now emitting signals shaped like human neural activity, then the distant intelligence responsible for the anomaly might no longer be studying humanity from 4,000 light-years away. It might already be learning how the human mind works, one thought pattern at a time.